And so, if I could heat the surface of, say, a 1035 steel rapidly enough so that the inside never even gets hot, then I could quench the outside and make it martensite, where the inside still stays as the ferritic structure. And we do this by something called flame hardening. So we take a lot of oxyacetylene flames, and say you have a big rolling mill roll, an embossing roll for a rolling mill, have a lot of oxyacetylene flames around the side with these tremendously high temperatures, and cause them to move up this cylindrical roll, and right behind it become sprays of water that quench it. And what we wind up with is maybe martensitic or almost martensitic structure in the surface of the material, where the inside of the material stays in its annealed state. So that's a surface treatment that's kind of difficult to control. It's better controlled in small pieces, and also better done when we do small pieces with an induction heater. Just like the induction furnace that was used to melt the metal in refining, if we have the little induction coil, say around a gear, and we cause it to be heated up, the characteristic heating will be from the surface inward. So the surface will heat up first. We put so much energy in the system, you can watch, let's say, a gear, a little spur gear, and you can watch it and it'll turn red hot on the outside of the gear, and you can still put your finger on the inside of it. And immediately they get it hot. They flow water through the tube that was surrounding it, that was the conductor in the little induction furnace. It has holes in it, so as soon as that gets red hot, you push a button or automatically it squirts water on the piece and quenches it and it becomes hardened on the surface. So they're induction hardened surface treatments, or flame hardened surface treatments, or mechanically hardened surface treatments. And we can do all of those things, but a better way perhaps is to put more carbon in the surface of a low carbon material, or to cause it to become imbibed in carbon, if you please, the very surface. And we have a totally new material at the surface. Now we do this in essentially two ways. Number one, we provide an atmosphere for the material that is going to be gaseous or liquid. And that gaseous or liquid atmosphere has to be capable of providing carbon or a material which will form a hardened surface. Is carbon the only thing that will give us a hard material inside the steel? The answer is no. We could put nitrogen in. If we put nitrogen in, we get an iron nitride instead of an iron carbide, and it in itself is hard. So we can cause nitrogen to flow into the steel just as we cause carbon to flow into the steel. Or we could put the two of them in together. And if we put the two of them in together, we call it carbonitriding, and we put it in. Well, let's just take for a moment carbonitriding. If we provide carbon atoms and nitrogen atoms in an atmosphere for this material that we want to case harden or surface harden, we have no difficulty at all in developing that product that we want. We could do it in a liquid by taking cyanide, say sodium cyanide, and liquefying it, and then quench the material in the sodium cyanide. Not quench it, I'm sorry, hold it in the sodium cyanide. And so the CN, both the carbon and the nitrogen of the cyanide, will diffuse in, and we get a carbonitrided surface. Could you do this in the solid state? Could you pack it in something solid and make it carburized? The answer is yes. You can pack it in materials that are easily decomposed, carbonates that are easily decomposed, so that you have a carbonaceous atmosphere that's developed. But it turns out to be a gaseous atmosphere that goes in contact with the metal, and the carbon is absorbed from it, even though you may use a solid state carrier. So we can pack carburized material in solid materials. We can put the materials in a liquid that has the elements in it that we want to surface treat with, or we can do it in a gaseous atmosphere. And so, for instance, if we wanted to just use nitrogen and we didn't want to use carbon in it, we could nitride a surface by cracking ammonia and having it available at the surface, and so it flows in. So this is the way that we are going to set about to do all of the operations that we can to give us the surface treatment that will allow us to have this composite type material that's really not composite, it's the same material, but we've just changed the characteristics drastically at the surface.
Mechanical surface treatment prevents fatigue by causing the outer surface of the material to be under compressive stresses. In an ordered structure, the alloying atom lies in the same exact position of every iron lattice. In a disordered structure, alloying atoms lie substitutionally at random in every lattice. Carbon can be added to the surface of a low-carbon steel by heating it in a carbon-rich atmosphere. Carbon content at the surface of a high-carbon steel can be reduced by heating the steel in an oxidizing atmosphere. Flame or induction hardening heats the steel's surface very rapidly and is followed immediately by quenching. The process occurs so rapidly that material under the surface does not heat up. Gaseous or liquid atmospheres surrounding a workpiece produce a surface or case with properties drastically different from the internal material.
Once you get that material developed, you immediately want to know how good a job did you do, because if your procedure isn't right, you may think you carburized, let's say, to a certain depth, and you may not have carburized it at all. So you need to be able to measure that. You will recall that when we talked about heat treatment, we talked about the Jominy hardenability test, where we quenched one end of the material, and then we examined along the length of the bar the hardness. So we stretched out the thermal flow effect, so to speak, or the heat treatment effect. When we want to look at the hardness under the surface of the material, we have a little bit of a problem. So we have to cut the material at a very shallow angle so that we're cutting through it so we can detect this hardness at the very surface, a fraction of a millimeter below the surface and a fraction of a millimeter below that. So in microhardness we get a distribution, and we will get a distribution which in a PV test, in a penetration volume test, the results will look just like a Sharpie test, except that we have on purpose expanded the measuring axis on this. And so we have to remember that we have to put that little magnification factor back in. It is apropos to look back now at something that we've studied, and that has to do with heat treatment, saying that if we want to get the maximum hardness out of a material, the maximum hardness out of a material is going to be provided when we have the maximum degree of quenching, the most severe quench. We have the right chemical composition, means that we're going to move the TTT diagram over to the right so we can get 100% martensite in the heat treatment. And 3, to have the maximum austenitic grain size. We want the grain size of the austenite to be as big as we can get it. Now later on we're going to talk about how to control grain size, but let's just say for the moment that we can control it, and we have inherently fine grain steels and we have inherently coarse grain steels. In this case we want an inherently coarse austenitic material. If you wanted to know what the austenite grain size was of a low carbon steel, you find it's very difficult to determine, because as the austenite cools, it precipitates out in great big blocks, the ferrite, and it sits in one corner. And so you couldn't find out what the austenite it came from, what its size was. On the other hand, if you have a hyper-eutectoidal steel, something in excess of 0.85, between 0.85 and 2% of carbon, you find that now when the austenite cools, the Fe3C is precipitated on the boundary of the austenite. So all you have to do is to look at the terminal structure, and the network of Fe3C describes for you the austenite grain size. Well, we need to know the austenite grain size for a hypoeutectoidal steel because we heat treat a lot of them. So how are you going to find out? Well, we play this little carbon diffusion problem, and what we do is we take a material that's low carbon, put it in a carburizing bath, cause the carbon to flow in it until the outside of the material is imbibed with carbon to the point that it's hyper-eutectoidal, and we cool it down and we look at the austenite grain size. We just take the same material that's there and make it hyper-eutectoidal by doing a case diffusion. And we're not interested now at all in the terminal material that we're going to have as a shaft or an axle or something like that. We're really interested in finding out how do we properly heat treat, or did we properly select our alloy for treating a hypoeutectoidal steel. And it's called a McWade-Ain test. Well, I think we should look at some of the properties that we get, or how fast or how far the material can diffuse into the iron. Because that's what we really want to do, is we want to have a hardness level that we can control below the surface. We don't want something to run all the way to the middle, and we don't want to wait a few years to have to get the carbon to where we want it. So if we start inspecting some of the diffusion characteristics, we find that if we took a characteristic carbon concentration versus distance for a given steel, this is an 8620 steel, and this particular steel now, we're going to look to see how far below the surface the carbon content has changed, and we find that on the very top surface of the material we get a rather high carbon content, and it begins to drop off, and it drops off rather rapidly. So we don't penetrate the material too far. Actually, it goes down measured in thousandths of an inch, but that may be good enough for what we want to do. But that penetration is going to be time dependent, and so what we really have to do is to look at something that has to do with the carburizing time. Now, if we do this and we look at the carburizing time for the material, we find that the time is represented in the abscissa, along the abscissa, for 3 different temperatures that we want to have: higher temperature, not quite as high a temperature, lower temperature, and a lower temperature in this particular case. And what we want to look at is the strength of the material, or the case depth of the material, or the strength of the material, and it plots out to look like this. And so we have, in this particular case now, we see what the time effect is. That is, the longer we wait in time, the deeper the case depth is going to be. Well, after you do this, what you're interested in, what the carbon percentage is going to be, how it's going to be distributed. And again, in this now, we're going to have a temperature variable. And we look at this slide for 1020 steel. This is like taking a very low carbon steel, a rather low carbon steel now. And we're going to do a carburizing treatment on it. And we want to find out what the carbon content is going to be along that penetration depth. And if we look at the distance below the surface of the material, we find that the carbon content is pretty high. It is hyper-eutectoidal up in this range, and it drops down to a pretty low value at a appreciable depth under the surface. Right? If we looked at this at a high temperature, we find that the carbon level that we would have at any position underneath the surface is going to be higher than if we carburized it at a lower temperature or a still lower temperature. So it's dependent not only on the carbon content now, is going to be dependent not only on the time, but the temperature at time, and it's also going to be dependent upon the alloy that we have. And so